I am Anne-Kathrin Baczko, an astrophysicist at the Max Planck Institute for Radio Astronomy in Bonn. My work focuses on so-called active galactic nuclei. In this video I will explain what an active galactic nucleus, short AGN, is. Let's start with the part galactic. This is an optical image of Centaurus A, a galaxy at the southern hemisphere with a dust layer covering part of the galaxy. Its activity is characterized by a strong emissivity over the whole electromagnetic spectrum. Its center can outshine the whole stellar emission. A subset of AGN reveal a stream of relativistic plasma, so-called jets, as is seen in the white panels at radio and X-ray observations. Overlaying all three images shows that the jets move out to distances by far larger than the galaxy itself. This leaves us with the part nucleus. For this we will have a closer look at our own galaxy, the Milky Way, and especially at its innermost center, the nucleus. By tracking the movement of stars around its center, the orbits can be derived. This enabled researchers to estimate the mass of the center of the galaxy, also called Sagittarius A star, to 4 million solar masses. This strongly supports the presence of a supermassive black hole at the center of a galaxy. But are there even more direct ways to verify that there is a supermassive black hole at the centers of active galaxies? For this we have to come back to Earth, where we are observing. I am here in Bonn, and just around the corner there is a radio telescope Effelsberg. One of the telescopes I use for my research. It is ideal as the atmosphere is opaque for radio waves, hence we can easily observe from ground. Secondly, with a 100-meter dish, Effelsberg is sensible to detect even the faintest emissions from distant galaxies. But the resolution of the telescope has some limitations. It directly depends on the dish size, and that can only be that large. The Effelsberg telescope, for example, has about the same resolution as our eye. However, to resolve the innermost centers of galaxies, it requires a telescope the size of the Earth. As impossible as this sounds, it can be achieved with a technique called very long baseline interferometry. By connecting telescopes spread over the whole globe, computationally, we build a virtual telescope with a dish of the size of the Earth. This provides the resolution required to take an image of the innermost region AGN. VLBI was used to take an image of the AGN in Messier 87. In the optical image, a straight, mysterious ray is connected to the nucleus. VLBI observations detect the jets also at radio wavelengths. In its center, the EHT collaboration took the first image of the black hole shadow with a size of about 4 times the solar system. This brings me to my last example. The AGN in the elliptical galaxy NGC 1052, a source in which I studied the peculiar double-sided jet. Being small for an AGN, its radio structure, including jets, is inside the optical galaxy. VLBI observations reveal a double-sided jet which is separated by a dark gap. It gets smaller towards higher observing frequencies and can be explained by absorption in a dusty torus around the central engine. Now we have all puzzle pieces together to draw a simple picture of an AGN. The enormous energy output of an AGN can only be explained by accretion of matter onto a supermassive black hole. This process forms an accretion disk around the central engine, and both together, black hole and accretion disk, can form the relativistically moving jets through electromagnetic processes around the central engine. But at larger distances to the black hole, a torus of dense, clumsy clouds forms. It, depending on our line of sight onto the source, this torus can prevent us from observing the innermost region of the jets in the AGN.